at least the first like one or two, those are kind of like applications of the multi-group diffusion theory that we already talked about. So like one and two should be relatively doable based on what we had already covered. And then the next couple of questions we'll get into today, and then the remaining questions, like the last, I think like four, five, and six, will be ones that we can do after next class. So hopefully those problem sets are going okay. Um, Hopefully after we saw exam one that we're like seeing some similarities between the problem sets and the and what you saw on the exam. So like my feeling with the exams are that if we are staying on top of those problem sets and doing all of those questions ourselves, yes, okay, it worked. Um, if we're staying on top of our problem sets, if we're doing those questions ourselves, then the exam was hopefully not too like hopefully there weren't surprises on the exam. Because a lot of those questions were pulled almost directly from the problem sets or were like maybe a variation of the like setup that you saw on the problem sets. Um, so before we got into like the content for today, I just wanted us to kind of think about where we're at with the class and to provide some possible help or at least suggestions for ways to like recalibrate if we feel like we need to. So like I I haven't graded exam one yet. My plan is to start that over the weekend and to either have that back to you like on Monday or have it back to you sometime next week. And so so even though you don't have your exam grade yet, after you like took the exam, you probably have like a decent idea about like I got that one right, I really messed that one up. So like you might have a good understanding or at least somewhat of an understanding of like what your expected grade was. Um, in terms of like the thinking about how to in terms of thinking about the point of the problem sets are like the main way that you're supposed to learn the material in terms of like, in class, we present the main information that you would need to then be able to like start the problem set and like succeed on the problem set. So like the lecture is kind of like a scaffolding from which you build up the to the point where you can start working on those problems. And then when you get like a quiz and when you get an exam, those are assessments, and assessments are designed to assess the knowledge that you've obtained through. Usually the quizzes is like kind of review of what was covered in the last lecture, or maybe like a short example that's like also similar to the lecture, or maybe similar to one of the problem set problems. And then the exams assess your knowledge over like a longer period of time. And so, one thing that I would consider is just like if you are struggling with the class, if you were finding that the exam was like more difficult than you were expecting, I would ask you to reflect on how much time you're actually putting into the class. Um, in general, these are like the general rules of thumb for like if you have a 3 credit hour course in a normal 16-week semester. The recommendation that I see a lot is 2 hours of class time spent for every 1 credit hour per week. So that means like if it's a 3 credit hour class like this class, and there's 16 weeks in the semester, and you're spending 2 hours of outside time per week per credit hour for a full 16-week semester, that works out to about 96 hours for the entire semester, but we're only in 10 weeks. So you take that and divide it by 10, and that's like about how much time you might spend on a class. And like obviously these are just kind of there's some variation that you could see here. Like maybe if it's an easier class, then you can get away with a lot less than this. But for a hard class like 304, I feel like that is about what I would expect. Like if you're doing the homework yourself, or sorry, if you're doing the problem sets yourself and you're like not using outside resources, like you're really grinding through every problem, you're sitting with the things that you don't understand, you're struggling with them, and you're like working through those difficulties, then like about 10 hours is kind of expected. So if we're spending a lot less time than that, and as a result of that, we're not understanding either the problem sets or the questions that we're seeing on the exams, then I would reflect on just like, am I putting in enough time for the class is like kind of one thing I would consider. And then I have some just general recommendations for how like I go through a class and also some of like what some things that I've learned from education research that I think are helpful to just be aware of. In general, like one of the main things that is illuminated by education research is that you learn best when you have chances to think and to write and to question and to respond and then receive feedback based on your answers and your responses to what you are being exposed to like in the classroom. And so whenever I'm setting up my lectures, I try to facilitate that. Like that's kind of the main motivation why I've set up my classes the way I do in terms of like giving you guys the slides with blanks so that you're able to like follow along. I try my best to kind of walk you through, like, I try to have us be walking through this process together versus it just being like the kind of lecture format where I'm just talking the entire time and like not asking any like questions to the class. So, I'm trying to do my best to like facilitate what I know works with learning, but you kind of have to be an active participant in the class to get the most out of it. And so being here on time is important and like being actually involved with the class. Like if you're here, that means that you're paying money to be here. And so like making sure that you're making the most of the time in class, I think is really important, being actively involved with the class. And yeah, so that's one thing that I would always recommend. Especially like I don't know, some of you might have already taken 304 with another instructor, some of you haven't. If you end up having to take the class again, you might not get a teacher that's as good as me. So that's the other thing just to consider is like best to like make the most of this opportunity now because there's a chance that it's worse the next time. But then also, in terms of like when to start those problem sets, when you leave class, you should be able to do like it'll vary a little bit from week to week and set to set, but you should be able to do like about half of those problem set questions when you leave class. And the best time to start the problem set is like as soon as possible after you've seen the material. That's when like if you're being actively involved in the class, you're thinking about it, you're processing some of that information. When you leave class is like when your brain is most primed to be able to start using the information. And that's what the problem sets help you do, is help you use the information that you've learned, apply it to problems that are going to build your understanding for what we're doing in the class. And so if you don't use it, you lose it. And that means that like if you think about your obtained knowledge, and if you go into a class and you're like really involved and you're following along with everything, then when you leave class, your obtained knowledge is kind of like at a peak. And the longer that you wait to use that knowledge, it's kind of like an exponential decay function as a function of time, where like the longer you wait, the more you're gonna forget. And so not using it means that you're going to lose it. And so that's why it's good to start as soon as you can so that you can start building on that knowledge and practicing the things that you're going to need to be able to like do well on the quizzes and on the exams. And so and at least like you might not be able to do every single problem and that's okay. You're probably going to struggle with some of those problems and that's okay too. Like struggling with material, especially in a hard class, is like kind of it's part of the process, I guess. And like if it was easy, then everybody would be nuclear engineers. But it's not easy, and we should expect that to be the case. We should expect to have to struggle a little bit. And so and part of that struggle is good. Like it might be frustrating at the moment, but working through those frustrations and like finally figuring something out is like really satisfying, especially when you can like know that you did that yourself and you didn't like when you start the moment that you started to struggle, you like looked up a solutions manual or you asked ChatGPT how to do the problem. So yeah, trying not to do that, trying to start as soon as you can, and the sooner you start, the sooner you're going to run into questions, and then the sooner that you can get those questions addressed. So like trying not to procrastinate is a good thing. And yeah, if you don't use that material, if you don't practice it, then you're gonna lose it. And so doing that after every class, and whenever you get stuck on something, letting me know. I've only had two people come to office hours for the entire semester, so like maybe that means that we're just like totally understanding everything and we don't have any questions, but I would think that that's probably not fully the case. So make use of those office hours. Like that's the best opportunity that you're going to have to be able to get one-on-one help with whatever it is that you're struggling with. And so if that means like if you want me to reteach something, if you want me to like walk you through a problem, I'm here to help. I want you guys to succeed. And so if you need help, please come and let me know. And there's no shortcuts to learning, just like there's no shortcuts. Like if you want to get really strong at the gym, you can't watch people lift weights. You can't like bring some device to like mechanically, like a thing to lift them up yourself. You have to put in like that work to build those muscles, and your brain is just another muscle. And so the way that you make your brain stronger is that you have to like really struggle through stuff a little bit and work through that stuff. So that's kind of where if you are quick to jump to things that are just going to tell you what the answer is, you might trick yourself into thinking that you've like learned it, but really you wouldn't know. You're not going to know it as well as if you struggled with that and tried to figure it out yourself. And there's like a fine line between struggling too long on something. Like if you've been stuck on a problem for like 30 minutes or an hour, that's when it's probably a good time to like move to another problem or to start asking for help. But if you started to struggle with it and then you just like jump to the answer, you might end up hurting your learning in the long run. And so these are just some like recommendations and some things to reflect on so that we are if any of this is resonating with us, if we're thinking like, yeah, I kind of have been doing that, maybe I should start sooner, maybe I should come to office hours, maybe I should be putting a little bit more time into the class. It's a good time to start reflecting on that now because at this point, we're there's still two more exams and the project. So there's still like a decent percentage of the grade that hasn't been assigned yet. And so like there's still time to recalibrate and readjust if we need to, but let's just make sure that we're being cognizant of that and that if we have questions or if we need help with anything, that we're making the effort to get that stuff taken care of. So hopefully that makes sense. If you have questions about any of that, as always, feel free to let me know. So today we're going to talk about slowing down theory. At this point in the class, like from exam one, we've talked about how what happens in a nuclear reactor basically just depends on the production rates and the loss rates of our neutrons in our system. And we've talked about how those production and loss rates are going to be based on all of the different the neutron nucleus interactions. So like our fission production rate and our absorption rate and our scattering, like in-scattering and out-scattering rates, which all require that we know the scalar flux, as well as the net leakage out of our system if it's like a finite reactor. And that means that we need our net current. And so once we have those pieces and we know how to compute those different reaction rates and loss rates, then we can start looking at how do neutrons distribute themselves in various situations. And so we've seen that in lots of different settings, like the bare infinite reactor, the homogeneous single region reactors and multi-region reactors, and then like different energy groups. And so and we've seen how you can kind of set up conservation equations to understand what the neutrons are doing in whatever setting you're considering. And so today, we're going to kind of pick up with the energy dependent side of the discussion. And we're going to use the energy dependent diffusion equations to get a better understanding of what neutrons do, specifically in the fast region and in the slowing down region. And that's going to help us better understand what's going on with the process by which neutrons are moderated or slowed down. And that'll also help us understand what kinds of materials make good moderators and help us better understand some of the things that we had talked about when we were talking about the neutron energy spectrum. So like when I say the neutron energy spectrum, at least for a thermal reactor, this is the plot that I was talking about. We've seen this before. We talked about how you can kind of break this up into like three different ranges where you've got like a in the lower energy range, this would be like our thermal range. In the intermediate range, this would be like the intermediate or like the slowing down range. And then in the high energy range, that was what we called the fast range. And so like the fast range is going to go from like 10 10 to the 4, maybe 10 to the 5 EV, all the way up to like wherever our cutoff energy is, which might be like around 10 MeV. Um, Neutrons are mostly born fast, right? That's what the fission spectrum shows us, is that like the most probable neutron energy coming out of fission is about 1 MeV. And so in the fast range, this energy spectrum looks kind of like that fission spectrum, and we'll do some math to show that that's the case today. Um, and then when we talk about the thermal range, when neutrons are in when we have a thermal neutron, it means that those neutrons are kind of moving around with an energy that's comparable to the average temperature of the materials in the reactor, like the moderator temperature. So thermal energies correspond to neutrons in thermal equilibrium with the reactor materials, and they have a pretty low energy. Like their energy is going to be less than 1 electron volt. So it's like the neutrons are born with 10 to the 6 electron volts, and they need to slow down all the way to like 1 electron volt or less to become thermalized, which is where they're more likely to cause fissions to make new neutrons. So neutrons have to lose a lot of energy to go from 10 to the 6 EV to 1 EV. They have to lose like over 99.9% of their energy to become thermalized. And so that's the other thing that we're going to talk about, is that slowing down process by which neutrons can go from fast to thermal. So the way that we're going to proceed is that we're going to look at the energy dependent neutron diffusion equation. So this was an equation that we talked about. I think it was in lecture 6. 5 or 6 is when I think we introduced it in 5, and then we applied it in 6 to develop that multi-group diffusion equation. So we're going to consider a bare and a homogeneous reactor, and this is the resulting energy dependent diffusion equation as an eigenvalue problem for that context. If the reactor is bare, what does that mean? Yeah, it doesn't have anything surrounding it, and so there's no reflector, and that means that we can basically say it's surrounded by vacuum. And if it's surrounded by vacuum, that means that if we were to talk about the flux at the extrapolated boundary of our reactor, and considering neutrons of any energy, that flux should be zero. If it's a bare reactor surrounded by vacuum, then the flux at the extrapolated boundary would be zero. And so that's what it means if it's bare. It means surrounded by vacuum or surrounded by nothing. Um, what does it mean if it's homogeneous? Same material everywhere, right? And so that's why in this equation, none of our material properties have like an R argument, because if it's a homogeneous reactor, then the material is the same everywhere. So you have no variation of your material properties from location to location within the reactor. So that's why you don't see any R arguments on our cross sections or on the diffusion coefficient. And so, yeah. And so this kind of equation, notice that we have a Laplacian, which means that it's telling us to take second derivatives of the flux with respect to space. But we also have these energy integrals. So our flux is technically going to be a function of position and a function of energy. And so we have this complicated integral differential equation because it has integrals and it has derivatives, and we need to try to solve it. And so if if we have like a partial differential equation where the solution that we're trying to find depends on multiple variables, what did we try before when we were looking at like the time dependent diffusion problem? What we did before is that we tried to separate variables, right? Like we assumed that if we have this flux, in this case it's a function of position and it's a function of energy. What we assumed is that we can kind of separate this function out into two parts. One part is like a space function that only depends on the position in our reactor. And then the other part is a energy. In this case, it would be an energy function, some function of energy that only depends on the energy of our neutrons in our reactor. So that's like a simplifying assumption where we're saying we've got these two, that the overall distribution looks like two distributions multiplied together, where one of them is just like a spatial shape function, and the other one is like an energy distribution function. So in that case, that's what f of e is. It's an energy distribution function. And then what we did was we took that definition and then we plugged it into our original equation, and then we tried to simplify the result from there. And so that's exactly what we would do is we would everywhere where we see phi of r and e, we replace it with this product question. Yeah, exactly. Before we had a spatial shape function and then a time evolution function. So here, it because this is an eigen problem, it means that we're looking at like a steady state problem. So that's why there's no d phi dt term. And so therefore the flux, we're assuming that the flux, when writing this equation, that the flux doesn't depend on time. But yeah, exactly. And so if we plug this in here, in some of these operations, like for example, the Laplacian operation, it only acts on space variables. So if we take the Laplacian of this product, the energy part can come out as a constant because the Laplacian doesn't act on energy variables. It only acts on the space function. And similar thing with all of these energy integrals, that if we put that function in here, this space function can come out of these energy integrals. So ultimately, what we're going to be able to do is kind of plug that in and then rearrange things to get an equation that looks like this, where basically we're plugging that in, we're dividing both sides by the phi of e and the r of r, sorry, the f of e and the r of r. So this is what results. And also, I'm on purpose, I'm moving the sigma t term to the other side. And so what ends up happening is that the way that we've kind of been able to manipulate this equation is that the left-hand side depends only on r. So the left-hand side depends only on position. And notice that the right-hand side, the way I've set this up, it only depends on energy. So the right-hand side depends only on energy. And if you have a partial differential equation and you do separation of variables, this is the point that you want to try to get to, where you have one side of the equation depends on one variable and the other side depends on another variable. And this is also the kind of form of the equation that we saw when we did the time evolution problem too, except one part depended on space and one part depended on time. And the argument that we made there was that if one side depends on space and the other side depends on energy, then we could change the energy value. Like we could evaluate the right-hand side of this function at different energies. And if I'm only changing the energy, that has no effect on the space part of this equation. So I might change the energies on the on the right-hand side, but the left-hand side is going to be unchanged when I do that. So if I can change the right-hand side energy values and the left-hand side isn't changing, that means that the left-hand side and the right-hand side are actually just equal to the same constant. Because I can make the same argument about the left-hand side. I could change the r position and I could evaluate this quantity at different values of r, but if I'm just changing r, it's not going to affect any of my energy quantities. So I could change the r values on the left side and the right-hand side is going to be unchanged too. And the only way mathematically that that can happen is if both of these equations, the left side and the right side, are equal to the same constant. And so just like before, we're going to call that constant Bn squared. So we can then use that fact to then break this problem up into two problems, where we have one problem that depends on space and another problem in this case that depends on energy. So I'm taking that energy, the space part, and I'm setting it equal to this constant. And then I'm taking the energy problem and I'm setting it equal to that same constant. And if I take this equation and I rearrange it by multiplying both sides by the shape function and then moving everything to one side, I get an equation that looks like this, which is hopefully familiar. And for the energy problem, what I'm gonna do on purpose is I'm gonna try to isolate this quantity. Like this quantity, these integral quantities is what I'm showing here on the right side of the equation, and I'm trying to move everything else over. So I'm gonna like add this term over. I'm gonna multiply both sides by f of e and by d of e. And as a result, on the left-hand side, I'm gonna have something that looks like this. I'm gonna have that diffusion coefficient as a function of energy times that bn squared. And then I'm going to have plus, and I'm going to have that sigma t of E. And that whole thing is going to be multiplied by that energy distribution function f of E. So I'm just doing algebra to rewrite the equation in this form. So now this is what my space problem is going to look like, and this equation down here is what my energy problem is going to look like. And we can proceed to deal with those two things separately. So when you look at that spatial problem, hopefully it looks familiar. Hopefully we recognize this is our favorite differential equation, which is the Helmholtz equation. And that's the exact same equation that we saw when we did this with a one group diffusion problem. And we've already solved this. We already know that for this equation, that B of n, those are my eigenvalues, and the R of n are my eigenfunctions. And we already know that the smallest of these eigenvalues is the one that corresponds to the effective multiplication factor and is the one whose eigenfunction corresponds to the fundamental mode eigenfunction. And we know that that smallest Bn squared is called what? The fundamental mode eigenfunction, that would be what the that would be like what the shape function looked like. And then the smallest of these BNs was called yeah, the geometric buckling. Perfect. So that's my BG squared, which is my geometrical buckling. So like we had that table, we even had it on the exam where there was the table of the BG squared values for the different reactor geometries, and then there was a corresponding flux shape, which was like the fundamental mode eigen function for those different geometries. And we call this the geometrical buckling because it's a quantity that only depends on the reactor's extrapolated size and shape. Size and shape. Right? Like like for all the different geometries that we considered, like for a cube and for a rectangular parallelepiped and for a cylinder and for a sphere, there was a different value that we had for BG squared. Like for a sphere, that BG squared looked like pi over r tilde squared. Right? So like if this was for a sphere, this BG squared, this geometrical buckling, only depended on the extrapolated dimension of the reactor. So it depends on the size, and then it depends on the shape, because depending on the geometry, there's a different formula for BG squared. So technically, there is some material property dependence on the geometrical buckling, and that's because this R tilde, when we talk about the extrapolated reactor dimensions, it's like if we had a sphere and this was like the actual physical radius of our sphere R, then when we say that it's a vacuum boundary, we're saying at some extrapolated distance away from the reactor, the flux goes to zero. So we're not saying that the flux goes to zero right at the boundary. We're imagining this like imaginary the extrapolated boundary is like an imaginary boundary around the geometry where we assume that the flux does go to zero. So here is where the flux goes to zero. And that distance to that extrapolated boundary, that would be my R tilde. And so there's this little distance between the actual surface and that boundary, and we can call that distance the extrapolation distance little d. And so technically, what we will assume generally is that that extrapolation distance is two times the diffusion coefficient. And we had already assumed with that diffusion coefficient that it was 1 over 3 sigma transport. You could also call it 1 over 3 sigma total if you don't know about the transport cross section. And so this sigma transport, it's a cross section. It depends on the materials in my reactor. So technically, if my diffusion coefficient depends on material properties, then my extrapolation distance depends on material properties. And that extrapolation distance is a part of my extrapolated dimension. So in that sense, the geometrical buckling does have a small um, material dependence, but generally, like if you have a big reactor, then the dimensions of the reactor, like this capital R, is going to be much, much bigger than this little extrapolation distance d. And so that means that that BG squared is mostly still determined by geometry. If it's a large reactor, then it's pretty much almost entirely dependent on geometry. But the smaller the reactor gets, the more that those material properties do like play some role in the BG squared. And so that was what we needed to know about the space problem. And then this is what we had for the energy problem. And this is equivalent to, if you look in the Svetkov notes, this is equivalent to this equation in the notes. So just to make sure that we're like kind of on the same page in terms of where our terminologies are. Um, and this energy equation is kind of like a neutron balance equation in that we've got terms on the left and terms on the right, and the terms on the left basically represent forms of losses, and the terms on the right represent forms of gains. Like this d times this bg squared, that's kind of telling me about like my net leakage. Um, and these are both multiplied by this energy distribution function. But like just like in the diffusion equation, when you see like d times bg squared, that's always attached to the net leakage term. The sigma t times this function, that's kind of like my total interaction term. Any interactions could technically result in my neutron being kicked out of like the current energy group that we're tracking. Just like neutrons could leak out of our system and therefore be out of the energy group that we're tracking. And so those would be technically losses. And then on the right-hand side, we have a term that's like a nu F, sigma F times this distribution, and we have our fission spectrum. So this is telling me about like fission production. That's my like production, neutron production term from fission reactions. And then this term right here is talking about neutrons that scatter from some other energy E prime into the current energy E that I'm tracking. And so this is like my in scattering term, my in scattering term. Neutrons that scatter into the current energy group E from some other energy group E prime. So, like physically, these terms have meanings, but they don't have reaction rate density meanings because of the units of this energy function. So they don't exactly have like reaction rate density units, but they still fundamentally represent different types of gain or loss mechanisms. And so the if we wanted to solve this equation, we'd be solving for this energy distribution. And that energy distribution, this is a homogeneous equation because every single term contains some multiple of that energy distribution. And so that means if f of e is a solution, then any constant times f of e would also be a solution. Like if I said that the solution for f of e was pi times f of e, and I plug that in everywhere, then on every term I would have that factor of pi, and it would just cancel out. So technically what that means is that the solution to this is only going to tell us information about the shape of the distribution. It's not going to tell us about like the amplitude of the distribution. Um, and so because of that fact, we get the freedom, oops, we have the freedom to normalize that condition kind of however we want. And we're gonna decide to normalize it such that this is true. And we do that on purpose because notice that what I've set equal to one is just kind of this term, right? That's that term in my equation. And so if that whole thing ends up equal to one, then my equation simplifies because then the only thing that's left over is my fission spectrum. So that when I make that assumption about how I normalize the energy spectrum, that means that I can rewrite my equation where I just have that fission spectrum term here. And the only thing we really have to be careful about is that this fission, because we want to be precise and we want to talk about units, technically this fission spectrum term, like if it was a normal fission spectrum, it's a probability density function, so it has units of inverse energy. But this quantity here technically has units. Like if we think about the units uh of nu, that nu, what are the units of nu? The nu sub f. This is like the number of neutrons per fission. Like for a lot of nuclides, that fission, it's about 2 point something. So this is the number of neutrons that come out per fission. What are the units of sigma f? Yeah, fission number of reactions per neutron distance traveled. And then this f of e function, it's going to be also an energy distribution function or like a probability density function. So it's going to have units of 1 over ev, but also dE is a energy is a little bit of energy, so it also has units of ev. So if I kind of cancel out the terms that I have, the neutrons cancel, the fissions cancel, and the EVs cancel. So overall, this quantity actually has units of inverse centimeters. So when I make this kind of connection here, I just have to remember that this term technically has units attached to it, which means that this chi of E is going to pick up those extra centimeter inverse centimeter units. So it's going to kind of represent like an effective neutron source term that has units of inverse centimeters per unit energy. Um, so yeah, hopefully that makes sense. It's just and so if chi of if this source term has units of inverse centimeters and inverse energy, that means that if we follow the units on the other terms, we should be able to see the same thing. Um, so with that being said, now that we kind of have a form of this slowing, so yeah, this right here, this is what we would call our slowing down balance equation. And again, it is a balance equation because it's showing us on the left-hand side our different losses, and on the right-hand side, it's showing us our different gains. And then in practice, what we can do is we can start trying to solve this equation in certain different contexts. So basically what we're going to do is just consider like a specific energy range, like only considering the fast range, and then we'll kind of modify the equation based on that energy range and based on what kind of physics would be involved in that particular energy range. So like as an example, we're going to think about the fast range. And all I've done here is I've rewritten that in scattering integral as just an in scattering source term, just like kind of for convenience. And then we can make the argument that if we're in the fast energy range, like energies above 100 keV, then the way that neutrons scatter, scattering is a reaction that can change the neutron's energy. And technically, a neutron could gain energy in a scattering reaction. So, like, but the way that a neutron would gain energy in a scattering reaction, like if a neutron is moving at another particle and they collide, the only way that the neutron could gain energy in that collision is if it was colliding with something that had more energy than the neutron did to begin with. So in collisions, the neutron gains energy if it collides with something more energetic than it. But if we're in the fast range where the energy is 100 keV, that means that those neutrons are moving so fast that there's basically nothing that they would collide with that would add energy to their energy in a collision. They would pretty much only lose energy in collisions at that energy. And so what that means is that in this energy range with energies above 100 keV, in scattering basically doesn't happen because neutrons would have to be colliding with something much more energetic than them to get kicked into that even higher energy group. So that in-scattering rate density is going to be relatively small. And if I think about the fission spectrum in the fast range compared to that in-scattering in the fast range, the fission spectrum is going to basically dominate. Essentially, what we're saying is that because of that first assumption, that this term is basically going to go to zero. So that's assumption one, that there's basically no in-scattering in the fast range. And then the next thing that we're going to assume is that the reactor is very large. And so if the reactor is large, like if we think about a sphere where BG squared is pi over r tilde squared, if the reactor is really large, it means that this extrapolated dimension is very large. And if the extrapolated dimension is very large, what does that mean about BG squared? It's going to get smaller, right? As r gets bigger, BG squared is going to get smaller. So that means that BG squared is going to be very small. And if BG squared is small, then if I think about this quantity right here, where I've got this D times this BG squared, and I've got this sigma T term, it means that this quantity is also going to basically go to zero. If BG squared is small and I'm multiplying some number by that small number, it's still going to be a small number. And especially what it really means is that compared to sigma T, that the sigma T of E is going to be much greater than the D times the BG squared. And so if that is the case, then that means that this term is basically negligible. The dBg squared term is negligible. And if that's the case, then really what this equation, all we have is the sigma t times the f of E, and that's equal to my fission spectrum. And so if I wanted to get an expression for this energy distribution, I would just divide the sigma t over to the other side. So this is going to look like 1 over sigma t of E times that f of E. Sorry, times chi of E. So, and notice this was written for the fast range. So what we're saying is that in the fast range, our neutron energy distribution looks like chi of E with a 1 over sigma t multiplier up front. So the energy distribution resembles the fission spectrum with a 1 over sigma t of E multiplier. And so that's helping to illustrate what I had been saying for a couple lessons about how in the fast range, the high energy range, that the energy distribution looks like the fission spectrum, and that's how you can show it. So hopefully that kind of makes sense and helps us to better see that I wasn't just making it up, but you can actually like work through like a logical process by which you could figure that out yourself. And so hopefully that makes sense. And if that makes sense, then that's awesome. And what we're going to do from there is in principle, we could go through a similar process to understand what's happening in the other ranges. Like the next thing that we want to talk about is what's happening in the slowing down range. And to do that, though, we have to talk a little bit more about scattering because scattering is the main reaction by which neutrons will lose energy to go from fast to thermal. So we got to talk about scattering a little bit. And when we think about scattering, I think it's a very helpful mental model to just think about like billiard ball collisions or like two like regular particles colliding with each other. Like if you imagine the neutron is moving and is colliding with a target nucleus that is at rest, then this is kind of just like a kinematic process, like even thinking back to like physics one, or I guess you did it probably in 302 as well, where you have like nuclear reactions and you look at everything at the beginning, everything at the end, and you write down some conservation laws for those reactions. Do y'all know what kind of physical laws would govern like a scattering reaction or like a collision reaction? Perfect. That's one of them, right? So we've definitely got conservation of momentum. Perfect. Yes, absolutely. Conservation of momentum and also conservation of the total energy. Total energy because technically with these nuclear reactions, you could have processes by which the state of the nucleus changes, and therefore you would have other kinds of energy like your E equals delta MC squared kinds of things if you have particles changing during the process. But yeah, and we talk about momentum, specifically, it would be linear and angular momentum. But yeah, absolutely. It's conservation of momentum and conservation of the total energy are be would be like the laws that govern these processes. Just like when you did collisions in physics one. It's a in some cases it can be a little bit more complicated, but this is a good mental model to keep in mind. And the main kinds of scattering that we will see, there's really like three main kinds, which would be elastic. We've got inelastic, and we've also got something called potential scattering, where with potential scattering, the neutron is scattering off of like the nuclear potential of the nucleus. So potential scattering and elastic scattering are kind of very similar. Inelastic is a little bit different. But yeah, we'll talk about these in a little bit more detail so that we can know the differences and know the significance of each type. So when we talk about elastic scattering and also potential scattering, these are the most like billiard ball collisions. And by definition of an elastic collision, it means that the kinetic energy of the particles involved is always going to be conserved. Kinetic energy gets conserved in elastic collisions. So if we use some notation like little n to denote the neutron, big N to denote the nucleus, I to talk about the initial state, and F to talk about the final state. Like if we imagine that we have a neutron with initial energy of 1 MeV colliding with the nucleus at rest, if it was an elastic collision that happens, it means that if I look at the energy, the kinetic energy before and the kinetic energy after, that they balance out, right? I have 1 MeV at the beginning, and in total, I have 1 MeV at the end. So yeah, elastic is like the main kind of reaction that we will end up seeing depending for pretty much all nuclei and also for most neutron energies, or at least the neutron energies that we care about. And in terms of the kinematics, it's helpful to think about like what happens if a neutron would collide with a small particle or with a large particle. And and in terms of like the collision analogy, you can think of the neutron as kind of like a marble, and you can think of a large nuclei like lead or uranium as kind of like a bowling ball. And so, if you have a marble colliding with a giant bowling ball, like imagine this same picture, but it's a neutron, it's a marble and a bowling ball instead of a neutron and a nucleus. Well, if that neutron comes in and hits a bowling ball that's at rest, the neutron is basically just going to like bounce right off, and the bowling ball is like barely going to respond to that collision. And so, what that means is that if the neutron collides with a very big thing, the neutron isn't going to lose a lot of energy in that collision. It can't transfer a lot of energy to that thing because the other thing is so massive. And so if it's a collision with a large nuclei, then the neutron is only going to lose a little bit of energy in that collision. Neutrons lose a little bit of energy in collisions with large nuclei. And hopefully that just makes sense from thinking about the marble and the bowling ball. But then imagine instead if you had a marble colliding with a marble. You've got one marble that's coming in and another marble that's at rest. And when they hit each other, both of those marbles are going to go off in different directions, probably with like about a comparable amount of energy after that collision happened. And that's because the marble can transfer a lot of energy to a thing that's of similar size to it. It's based on the relative masses of the particles. And so if it's a collision with a small nuclei, then the neutron can lose quite a bit of energy in that collision. An example of a small nuclei would be like hydrogen. Like if you think about a neutron, it's just It's just one neutron. And if you think about hydrogen one is just one proton and no neutrons. And so it's basically like a neutron colliding with a proton, and both of those things have very similar masses. So if a neutron collides with hydrogen, it can lose a lot of energy in that collision, because the hydrogen is about the same size as the neutron. Um, and so, yeah, this is kind of like the principle that we want to keep in mind. And we're going to do some math to show that that is indeed the case, that there's a big dependence on the atomic number or the size of the nucleus that's participating in the collision process that will allow us to get better, allow our neutrons to lose a lot more energy in these scattering reactions. So that's what we're going to talk about more today. Elastic is very similar to inelastic, except the main difference, it's still like a collision, but the main difference is that the kinetic energy of the particles is not conserved with inelastic scattering. When you did collisions in physics one, if you did inelastic collisions, those were collisions where the kinetic energy isn't conserved because that energy ends up going somewhere else. Like if you've got a car crash where like one car crashes into another car, and in that process, one of the cars gets like broken and mangled and deformed, energy has to go into breaking those materials that doesn't end up going into the kinetic energy of the objects. And so in like the nuclear context, it's kind of similar that like if we imagine the neutron is coming in with 1 MeV and colliding with the nucleus at rest, and then if the neutron comes out with like half an MeV, and the nucleus has like a kinetic energy of 0.3 MeV, that means there's 0.2 MeV that's been left out. And in that case, in this case of an inelastic collision, that 0.2 MeV is going to go into the excitation energy of the nucleus. Like the nucleus is going to get hit and then it's going to get excited and it's going to have some extra excitation energy because of that collision. And when a nucleus gets excited, eventually it'll come back down to like its ground state. And when a nucleus goes to its ground state, it emits a particle. Do y'all know what kind of particles nucleuses emit when they lower their energy level? Perfect. Gamma rays. Awesome. Yeah, exactly. They emit gamma rays. There's kind of an analogy there between electrons, and that the electrons in an atom, if an electron gets excited, it can get kicked up to a higher like orbital level. And then when that electron settles back down to its original energy level, that energy difference gets resulted in an X-ray getting kicked out of the electron cloud. In the nucleus, there's a nuclear structure, and this excited nucleus corresponds to some nucleon in the nucleus getting kicked up in an energy level. And then when that nucleon settles back down, it emits a gamma ray instead of an X-ray. Um, and so in general, elastic scattering is relatively uncommon, but it happens more if it's a high Z nuclei, like a nuclei that has a high number of protons. And also with high energy neutrons, it's more common as well. Um, and so in terms of fusion, in terms of fusion reactions and fusion reactors, this is a challenge. Um, because like even in regular fission reactors, where the most probable energy of the neutrons coming out of fission is like 1 MeV, shielding those neutrons is no easy feat. Like you could have an entire career as a nuclear engineer just doing shielding design. And it's a combination of both having to shield those neutrons as well as having to shield the gamma rays that come out of these different processes, like inelastic scattering. And if you think about fusion reactors, um, just like there's a big difference in the energy going from chemical reactions to nuclear reactions, like nuclear fission reactions, there's a comparable energy difference in the energy coming out of fusion reactions compared to fission reactions. So the neutrons that come out of fusion come out with like 14 MeV versus 1 MeV. So it's like an order of magnitude more energetic. And those higher energy neutrons are going to participate in inelastic scattering, which is going to result both in them um, which is going to result in them creating very high energy gammas. So the gamma rays that come out of fusion reactions are even more harder of a challenge, which just is another kind of thing that the fusion people are going to have to figure out. Um, I wouldn't like test you on this or anything, but if you're interested in fusion, this is a good paper that kind of talks about some of the challenges of designing these reactors from like a shielding perspective. So elastic scattering is the main kind of scattering that we're going to be talking about in terms of the most common reaction that we're going to see for scattering. And when we think about scattering, like elastic scattering, it's just kinematics. And so, like the picture that we were just showing is kind of like the picture that we're probably most comfortable with when we think about a scattering reaction, where those are usually done in the lab frame, where it's kind of like you're in the lab and you're watching this process um, you're watching this process take place. And so you're kind of free with kinematics to choose your choice of coordinate system. And it just so happens that using these calculations in the lab frame ends up being a lot more complicated than if we were to convert to something called the center of mass frame. And so um, that that's what we're talking about here, the center of mass frame. And in the center of mass frame, you it's perfectly valid to go from the lab frame to the center of mass frame. You just have to do the proper like conversion. Um, and in the center of mass frame, instead of the basically what that means is that we're assuming that the center of mass of the particles that are colliding is treated to be at rest during the process. And so you don't have to, in my class, you don't have to do calculations in the center of mass frame, but we do need to know about some of the results that come out of this process. Um, so we're going to define something called capital A, which is going to be based on the mass of the nucleus divided by the mass of the neutron. And the mass of the nucleus divided by the mass of the neutron is going to be pretty close to, but not exactly equal to the atomic number of the nucleus. So like we've got a neutron here with mass little m, we've got a target nucleus with mass big M. Capital A is the ratio of the mass of that nucleus to the mass of the neutron, which is almost the same as the atomic number of the nucleus, but the mass of the neutron isn't exactly one, so technically they're a little bit off. If you're doing like real reactor calculations, you would probably want to use the exact value of A. In this class, in back of the envelope calculations, it's totally fine to just assume that A is the atomic mass of the nucleus, which is something that you would just know from like if it's hydrogen 1, then the atomic mass is 1. If it's uranium 235, then the atomic mass is 235. Um, and so if and we don't need to derive this equation. This equation is worked out in the notes, but basically this is showing how the initial energy of the neutron relates to the final energy of the neutron if you have a scattering reaction in the center of mass frame. So this is what the particles look like before the collision. This is what the particles look like after the collision, where this theta c is this little scattering angle that the neutron is coming out with in this scattering reaction. So the final energy of the neutron, it's going to depend on its initial energy. It's going to depend on that scattering angle, and it's also going to depend on this parameter called alpha. And by definition, alpha is just that big A minus 1 over that big A plus 1, and this whole thing is squared. So in principle, if we know what the nucleus is that the neutron is colliding with, then we will know big A. If we know big A, we can calculate little a, and then that was what would go here. And the only thing that we would need to find information about is that theta c. What's like the scattering angle that neutrons are coming out with? And so if we look at that result, like I was saying, like we don't need to spend time deriving this. It's in the notes, but and so I wouldn't ask you to derive it, but I would ask you to like be kind of familiar with this equation and to certainly understand like the different parts of it. So EF is the final energy of the neutron in the lab frame. EI is the neutron's energy before the scattering event, also in the lab frame. And theta C is that scattering deviation angle in the center of mass frame. And so, like in principle, if we were like doing an experiment, and this is a nice equation because the energies are really what we care about, and those are already in the lab frame energy in lab frame reference, which would be like the energies that we cared about. Like if we were doing these measurements in a lab, we would be able to measure the EI and the EF using like a neutron detector, and the only thing we would need is this theta C, and that theta C is going to come from other experiments that people have already done. And those experiments will already have that theta C be in the center of mass frame. So that's kind of how we can make use of this equation. And so if we're thinking about like kind of just redrawing the picture, we've got like our neutron coming in and colliding with our nucleus. And and kind of the question that we want to think about is how does that scattering, and this neutron has an initial energy EI, and we kind of want to think about what kind of scattering reactions, what kind of deviation angles would result in my neutron losing losing a lot of its energy or losing very little of its energy. So if it comes in with an energy EI, it has a scattering event, and we basically want to ask the question, what's the most amount of energy that the neutron could have after that scattering event? And oops, and what angle would that correspond to? And so if the neutron comes in with an energy EI, the best thing that it could do is just kind of like have a collision where it just grazes right past the nucleus. And so that would correspond to a theta C of 0. So if the theta C was 0 degrees, that would be like a grazing collision where the neutron just kind of like grazes right past the nucleus. And if my theta C is 0, then I have cosine of 0 here. What's cosine of 0? Cosine of 0 is 1. And if this is 1, then notice the alphas have opposite signs. So the alphas would like subtract away. And I'm going to have a 1 plus 1, which gives me a 2. And that 2 would cancel out with this 2 down here so that my final energy would be exactly equal to my initial energy. So my final energy that I could have, the maximum final energy I could have, would just be the energy I started with if the neutron just comes in and has like a straight grazing collision with that nucleus. It kind of stands to reason that if coming in with an angle of coming in and then coming out with an angle of 0 is the most energy I could have after that collision, then as I increase that scattering angle, I'm going to lose more energy in that collision. And as it turns out, the most energy that you could lose would come from a collision where the neutron comes in and then gets kicked back out in the opposite direction that it started with. So that would mean theta C equals 180 degrees or pi. And that kind of scattering event would be called a backscatter, where the neutron comes in and then comes out in the exact opposite direction that it went in with in the first place. So if my theta C is pi, what's cosine of pi? -1. Unit circle. And on the unit circle, the cosine is like my x value. So at 0 degrees, it's 1, and then at pi degrees, it's -1. So if I have a -1 here, then that means the sign on these two terms gets switched. So like the 1 becomes negative and the alpha becomes positive. So now the 1's subtract away, and the alphas add together to give me 2 alpha, and then the 2 up here cancels the 2 down here. So my minimum possible energy would be alpha times EI. So notice the minimum energy I could get out of that collision is going to depend on the value of alpha. And if we want the minimum energy to be as low as possible, that means that alpha should be like a small number, right? Alpha should be a very small number if we want to lose a lot of energy in that collision. And if alpha needs to be small, that means that big A needs to also be small. Like if you think about hydrogen, that means that A for hydrogen is 1. And if I plug in A equals 1 here, then I have 1 minus 1, which is 0 over 2, and it's squared, but it's 0 up top. So that means alpha equals 0. So technically, a neutron could scatter off of hydrogen and lose all of its energy. That's the most it could lose is all of it, because for hydrogen, that alpha would be 0. And you can imagine that if the alpha, if the nucleus is higher, then alpha will be closer to 1, and then you would lose very little energy. Like if you used uranium 235, then A would be 235, and then alpha would be 234 over 236 squared, which is going to like be basically 1. So when that neutron scatters off of uranium 235, it's going to like basically lose no energy in that collision. And so doesn't that agree with what we were saying before, that the neutron is going to lose the most of its energy when it collides with things that are small size, like compared to it? So like the the basketball or the bowling ball marble analogy kind of holds true even when it's like actual neutrons and nuclei. And so once we understand that result, then we can talk a little bit more about how we can actually use probability understanding to move forward and do some calculations. So when we were talking about that differential scattering cross section, remember that this differential scattering cross section is our regular scattering cross section times a probability density function. And this probability density function characterizes the likelihood of a scattering collision taking me from some energy EI to the final energy EF. And so this product is the differential scattering cross section, which tells me about the expected number of reactions that result in my energy changing from EI to EF per unit neutron distance traveled and per unit energy. And what we were just saying is that that final energy that I come out of that scattering reaction with is going to depend on the distribution of my nucleus, or sorry, the distribution of my neutron and what angle it comes out of that scattering reaction. So therefore, we would kind of, to get this probability density function, we would need to know something about the probability density of the neutrons that come out of my scattering reaction with a certain deviation angle theta c. And so I have some plots that we can look at to better understand for different nuclei how their angles get distributed at various energies. So these are some really cool plots that we should be familiar with. On this axis is the energy. So that's like the energy EI. That's the incident energy of the neutron. And so the way you read it is that you ask yourself, like, what energy am I at? Am I at this given energy? And then I look to this rest of the plot. And so on this vertical axis, it's a probability divided by the cosine of the angle. And this is the cosine. So when we say cosine, it's the cosine of theta c. That's what when we mean when we say cosine. And so notice that if cosine equals 1, which would be along this line, that corresponds to theta c equals 0. And if cosine is -1, that corresponds to this line. And on that line, that's theta c equals pi. So these are grazing collisions along this line. These are backscattering collisions along this line. Obviously, cosine of 0 would mean that you scatter and you come out at 90 degrees from where you started. So you look at the various like if my neutron has an energy of 10 to the 4 eV, then this is kind of showing me what's the probability of my scattering reactions coming out at various angles. And so this is for hydrogen 1. And notice that for hydrogen 1, it's a flat plot. For every single neutron energy, this probability is constant. It doesn't matter what the resulting angle I come out at, it's an equal probability to come out at any different angle. And so that means that the scattering for this nuclei is isotropic, and that the angles that I come out with have an equal chance. I have an equal chance of coming out of that reaction at any different angle. And we call that isotropic. This is what isotropic scattering would look like. It's also called S-wave scattering. So hydrogen is a perfect S-wave scatterer. It's always going to do isotropic scattering. But not all nuclei are as nice as hydrogen. This is a plot of natural carbon or carbon 12. And so notice that this is on a log scale, right? So if this is 10 to the 6 EV or 1 MeV, then this would be 2 MeV. And then that would be 3 MeV, 4 MeV, 5, 6, 7, 8, 9. And then once I get to 10 MeV, that's the same thing as 10 to the 7 EV. So, but notice that like past around 2 MeV, that the scattering for carbon goes from being basically an S-wave scatterer to having these like crazy complicated, like oscillating places where in some at some energies, it's more likely to have a backscatter. At some energies, it's more likely to have a grazing scatter, and it kind of oscillates back and forth depending on the energy. So what's happening in this region is like pretty complicated. This is all about there's lots of quantum effects that like if you want to really understand why these plots look like that, you have to understand more about quantum mechanics than I do. But that's kind of what's going on here. But notice that this is really only happening at energies above 2 MeV, and that's kind of most of our neutrons are not going to have that energy. And so, for carbon, you could basically consider it an S-wave scatterer too. And like we care about hydrogen because that's part of water, and that's why we like water as a moderator. But also a lot of reactors use graphite as a moderator, and that's what carbon 12 is. Graphite would be made out of carbon. So we care about carbon. We care about oxygen too, oxygen 16, because water is hydrogen and oxygen. And so notice that if this is 10 to the 5, this would be 200 keV. And around 200 keV is where we kind of deviate from S-wave scattering to having those oscillating peaks and valleys. So for oxygen, it deviates from S-wave scattering around 200 keV. This is for uranium-238, and it deviates from S-wave scattering around 50 keV. So that would be like around here. And uranium-235 is 238 is interesting because it becomes heavily forward peaked, which means that like at energies above 50 keV, notice that becomes more and more likely that the neutron just like has a grazing collision where it just like kind of goes right past it, and backscattering becomes relatively unlikely. So yeah, these are just some plots that would kind of for any nuclei, you could find these plots on like a nuclear energy database. And it is from these plots that we could develop in a relationship for that probability density in terms of that scattering angle. And so S-wave scattering is like our favorite kind of scattering, mostly because it's the scattering reaction where we can actually do analytical calculations. And so the probability density for S-wave scattering, what it means is that just like we were seeing in that plot, S-wave scattering means that the neutrons that come out of that reaction have no preferred direction. They have equal chances of being scattered in different directions. And so that's what we refer to as isotropic scattering. The scattering is the same in all directions. And if it's S-wave or isotropic scattering, then this is the kind of probability density function that we have. And this is basically the exact same way that we sketched this out when we were talking about the first introducing the differential scattering cross section, where EI is the is the incident energy, and that's basically the best that we can do is to come out of that scattering reaction with the same energy we started. We said that there would be some minimum energy below which we wouldn't find neutron scattering with any lower energy than that. And now we have shown that that is equal to alpha times EI from our talk about scattering in the center of mass frame. And this is the most common form of scattering that we have in nuclear engineering. Um, and yeah, what it basically means is that for these different energies that our neutrons come out and corresponding different angles that they come out, the probability is constant. Um, and so, yeah, this is very, very accurate for neutrons, certainly in the slowing down range. Like all of those nuclei that we were just looking at for neutrons between like less than 50 keV, they were they were basically S wave scatterers. And for light isotopes like hydrogen, oxygen, carbon, it's also pretty much always going to be S wave scattering, certainly in the slowing down range. So within this energy range, and for especially for light nuclei, we mostly see S wave scattering. So that was our detour into talking about scattering in more detail. And now that we know about S-wave scattering, we have a way to characterize the probability density for those neutrons that participate in S-wave scattering. And therefore, we could plug this in to our equations to be able to get more to move forward with the solving process. So just returning down to that slowing down balance equation that we had, and we're now going to solve this for a special case, which would be an infinite medium of pure hydrogen. So if it's pure hydrogen, that means big A is 1. And therefore it means alpha equals, oh, I meant to say that here. Alpha equals 0 if big A equals 1. And for hydrogen, at least in the slowing down range, we can assume that there's no absorption, which means that sigma total would just be sigma scatter as a function of energy. It means that sigma A is basically 0 in the slowing down range. For hydrogen, it's true that it's basically it doesn't do inelastic scattering. It's a perfect S-wave scatterer. Um, and that's point number 4, that its scattering is isotropic. We're going to assume that there's no neutrons that have an energy above some cutoff. You're kind of free to decide where that cutoff is. For us, like for fission reactors, it's about 10 MeV. So no neutrons would have energies above that 10 MeV cutoff, and it's an infinite medium. So, so what would BG squared be for an infinite medium? Yeah, perfect. Like if we think about a sphere, because it's just the easiest one to write, that BG squared is pi over r tilde squared. And so if it's an infinite medium, as this goes to infinity, BG squared goes to 0. And so this is like the simplest case that we could start with, but it's a case that we could still learn a lot from. So that's kind of why we pick this approach. And so with all of this being said, we can start moving forward with our problem. We had already said, like, this is what our probability density function is for an S-wave scatterer. And we just said for hydrogen, alpha is 0. So if alpha is 0, then this probability density function just looks like 1 over EI. And then if we kind of what I've done here is I've also simplified. This was my d times bg squared term, but it went to 0 because bg squared went to 0 for an infinite medium. And this now is what my if I just go back real quick, this sigma s from e prime to e, we just said that that's going to be sigma s times this guy is sigma s at e prime times the probability to go from E prime to E. And we just said that this probability to go from E prime to E is just 1 over that incident energy, which would be 1 over E prime. So that's kind of how I'm simplifying to get here, right? I've got my sigma S E prime up top. I've got my f of E prime still there. And then 1 over EI becomes 1 over E prime, just kind of switching back to the notation where prime was the initial energy and then regular E is the energy we're keeping track of. So that's what my slowing down balance equation becomes. And then we're going to, by definition, assume the collision rate density, which is F of E, is just defined as being sigma T of E times my energy distribution function. And then we're going to assume that sigma A is zero, as we said, which means that sigma T becomes sigma S. So this is going to look like sigma S of E times F, little f of E. So what I'm going to do is I'm going to use that definition right here. And that on the left-hand side, I'm going to have this product, sigma S times little f of E, which is my big F of E. And then nothing is changing with chi, so I'm still going to have a chi of E. And then I'm going to have this integral going from E to that cutoff energy E0. And then by definition, notice that this sigma S of E prime times this little f of E prime is by definition big F at E prime. So I'll have a d E prime times a big F of E prime divided by E prime. So this, after we make all of those assumptions, plug them into our balance equation, this is what we can write in terms of our collision rate density. And this equation is kind of complicated. It's complicated because we're trying to solve for f of e, but f of e is also inside of this integral. And so I'm just going to kind of in a hand wavy way, say that there's an analytical. Oh, question? Mhm. It's kind of we've redefined it so like they're equivalent in that if I wanted to take f of big E and recover that energy distribution, I would just divide by sigma s. So I'm just kind of using this substitution because that substitution is what allows me to have an analytical solution to this integral. But then in the next slide, I'm going to convert back to little f of e. Um, but yeah, so technically they are related though. So there's an analytical solution to that integral, which looks like this. And then the next thing that I'm going to do is just rewrite it as the recover back that original energy distribution little f of e by dividing through by sigma s. So if I take big F of e and divide by sigma s, I get little f of e. If I take chi of e and divide by sigma s, then I just get chi of e over sigma s of e. And then I'm going to be dividing this term by sigma s of e, which is just going to end up being a constant a multiplier that comes up front. So I'll have 1 over e times sigma s of e times that integral from e to e naught dE prime chi of e prime. So now this guy right here is my energy distribution for hydrogen, for an infinite medium of hydrogen with no absorption. And so the next kind of thing that we have to do is think about our fission spectrum. And we're just going to make the argument that between some energy E star and our cutoff energy E0, that there's no fissions that occur outside of that energy range. Like if we consider the fast range and we say E star is about 100 keV and E0 is 10 MeV, within that fast range, we can have neutrons that are produced from fission. But outside of that specific energy range, the chi of E is basically going to be zero. So if I consider energies above E0, no neutrons are born at energies above the cutoff. So my energy distribution just looks like zero there because chi of E is zero and this integral would be zero outside of the range where it's defined. If I look at within this fast range, my distribution is basically just unchanged. I can't really simplify it at all to so this is my distribution in the fast range. And then if I consider neutrons with energies below this E star, then outside of that range, chi of E is going to be zero as well. So this first term drops out. And then for the second term, I still have to integrate from my current energy, which becomes E star, all the way up to E zero. And so by definition, if I'm integrating the fission spectrum over that over its entire range where it's defined, that means that this entire integral is just equal to one. And so that means that this entire thing in the slowing down range is 1 over E times sigma s of E. So and this is in the slowing down range. And that's a really important result. And that was exactly what we were seeing on our original plots of like flux per unit lethargy or that energy distribution, that in that slowing down range, the energy distribution looks like 1 over E. Because in this range, sigma s is also basically a constant. So it's basically just some constant times 1 over E. And so that's kind of why it's nice to do this for hydrogen, because it's a simple enough problem that we can like work through the math and still make some reasonable conclusions that agree with what we had seen before. In principle, you could do the same process for more complicated problems, and you would see slightly different results, but the overall trends would be the same, and that you would still end up seeing that the slowing down range follows 1 over E. You would see that the fast range follows the fission spectrum, and really all that would change if you did a more complicated problem was that you would have more complicated multipliers attached to that overall trend. Um, and so yeah, that was what I wanted us to see for slowing down for hydrogen in an infinite medium. Um, and from there, I wanted to kind of do a little bit detour into understanding more about what different materials make good moderators and introduce some figures of merit for being able to evaluate is a different material a good moderator or not. So lethargy, which is a symbol, we use the symbol little u for lethargy, is a quantity that we can use in replace of talking about energy. And so when we talk about lethargy and we use the symbol little u, by definition, the lethargy u is defined as the natural log of some reference energy E zero divided by the current energy E. So essentially, what we want to think about is that if you have an energy axis where this is like 0 and this is like 10 MeV, that notice that so E0 is our cutoff energy. So if we were to write a lethargy scale, when E is so if we say E0 is 10 MeV, then at that energy of 10 MeV, our lethargy U is the ln of 10 over 10, which is the ln of 1, and ln of 1 is 0. So neutrons have 0 lethargy at the energy where they're born, which would be the E0. And as the energy E decreases, the ln of this quantity would increase. So lethargy moves in the opposite direction of energy. And that as the neutron energy decreases, the lethargy increases. Lethargy means like being lethargic, means that like you're slow. Like sometimes when I wake up, I feel lethargic because I don't want to get out of bed. And so it's just a measure of kind of like a measure of the slowness of your neutrons. And we use lethargy because it simplifies things. Lethargy is also sometimes a nice quantity to work with because lethargy has no units. Like if you think about lethargy is an ln of a is an ln of a fraction. Ln has no units, and this fraction, whatever units were inside, would get canceled. So there's no units associated with lethargy. And yeah. And so this is what we were saying is that when that neutron is born, it has a maximum energy, and that corresponds to a lethargy of 0. And then from this picture, what we were saying is that as the energy decreases, the lethargy increases. So as E decreases, U increases. And if this is the formula for lethargy, then we can talk about the change in lethargy. So U final minus U initial would be the change in lethargy. And this E just corresponds to the energy. There's a one-to-one ratio between lethargy and energy. So at any energy E, I have a corresponding lethargy U. And so if I have an E, I would have an E final for the first term. I would have an E initial for the second term. And then because of properties of logs, I can rewrite this as just the ln of EI over EF. And so, whenever I was saying that there's a one-to-one relationship, we could like take this equation and solve for the energy big E. We would like take the exponential of both sides to clear the logarithm, and then we would move the E to the other side, and we would divide the E to the U to the right-hand side, and what you would end up with is that big E is equal to that energy E0 times exponential minus U. So for any neutron energy E, I can compute the lethargy, and for any lethargy U, there's a one-to-one relationship between these quantities. And with this definition, you can take any of the quantities that we had already talked about, like any energy dependent quantities, and rewrite them in terms of lethargy instead of being in terms of energy. So that's like the way that you change variables to go from E to U is what I was going to show next. When you do this change, you just have to mostly be careful about the units because lethargy is unitless. So like if you're taking a reaction rate density in energy and converting it into a reaction rate density in lethargy, then the lethargy units would not have the EV attached to them, whereas the energy term would. So like if we wanted to talk about a lethargy dependent collision density, big F of U, it would be related to the energy dependent collision density F of big E, and we would just have to conserve reaction rates. So the collision rate density and energy has to represent the same thing as the collision rate density in lethargy. Like if the collision rate density in energy terms is some number of reactions per unit volume per unit time, that has to match if I switch over to a lethargy scale. Otherwise, my math won't make sense. And so the way that we make this work is we include the appropriate multiplier to make sure that the overall units on each side match. And we also include a minus sign up front because of the fact that as E and U move in opposite directions, as energy goes up or as energy goes down, the lethargy goes up. So that's why there's the minus sign there. And so if we take this definition, which is how we would write the collision rate density in energy and the collision rate density in lethargy, and we get F of E divided by F of U, it means that we're like dividing by F of U and we're also dividing by dE. So this would be negative dU over dE. And U, we have a definition for the lethargy U in terms of the energy E, right? By definition, I have negative, I have d by dE of that lethargy U, and that lethargy U is the ln of E0 over E. And this derivative might look complicated because it's like, uh-oh, I've got the derivative of a natural log with a fraction. But if we think about our log properties, remember that ln of E0 divided by E. Because of log properties, if you have the ln of a ratio, that's the exact same thing as the ln of the difference of those two terms. Like, in other words, this is the same thing as ln of E0 minus the ln of E. And so if I'm taking the derivative of this with respect to E, it's a lot nicer because the derivative of this first thing with respect to E is just a constant. And then if I take the derivative of negative ln of E, well, we know that if I integrate 1 over E with respect to E, I get the ln. So if I do the opposite and I take the derivative of ln of E, I get 1 over E. So this derivative of this quantity is going to be negative 1 over e, and I've already got a negative sign up front. So overall, this just becomes 1 over e. And therefore, if I want to talk about my collision rate density in lethargy, f of u, I'm just going to get this by itself, which means I'm going to end up with e times big F of e. So this is the way that you can convert from a collision rate density in lethargy to a collision rate density in energy. You just take the energy dependent collision rate density and multiply by big E. And if you could go through a similar process to convert the flux as a flux per unit energy to a flux per unit lethargy, and it's going to look basically the exact same. It's going to be the energy E times the flux as a function of energy. Um, so that's how you convert these kinds of like integral, like reaction rate based quantities. If you convert cross sections, you don't have a factor of E up front because cross sections aren't a density and energy. And therefore, you can always just have a one-to-one relationship between the energy E and the lethargy U. And if I have a table of properties, a table of cross sections at various energies, I can use my lethargy equation to say at each energy, what's the corresponding lethargy? And then I could remake that table to be in terms of lethargy instead of terms of energy, and there wouldn't be any extra factors in that conversion process. Um, there is some extra quantities that we can talk about that we basically define in terms of um, the lethargy. So technically, we can define this change in lethargy, the final minus the initial. Sometimes it's called the logarithmic energy decrement because, like what we were just saying with log properties, that if this is the same thing as ln of EI over EF, that means I'm doing ln of, I could also write it as ln of EI minus ln of EF. And yeah. And so this quantity right here is the logarithmic energy decrement. There's another thing that we like to talk about, which is the average lethargy gained per collision. And we call this lovingly, we call it worm, or sometimes you call it squiggle. But it's the Greek letter C, which is this guy right here. So he kind of looks like a worm or kind of like a squiggle. That by definition is the average lethargy gain per collision. So it's like we have the lethargy change, which is the ln of EI over EF, and it's an average because we're integrating it with some weight function, where in this case the weight function is the probability density function that takes me from energy EI to the energy EF. So this is by definition how we define worm or squiggle. And you can't really evaluate this integral except in special cases where you know what this probability density function is. So like for S-wave scattering, we know what that density function is, so we can plug it into our integral. We can get an integral that is analytically solvable. It kind of looks complicated, but the way you would do this is with technically it's U substitution, but you've already got a U in terms of we're using U for lethargy. So in this problem, I called it X substitution, but you substitute in X equals EF over EI, and that allows you to get a analytical form of this integral that is relatively easily solvable. And so this expression right here is a way that you can actually calculate the lethargy gain per scattering collision if the scattering events are involving a S wave or isotropic scatterer. Um, and so, yeah, that was really everything that I wanted to say about today. This next thing just talks about two different like ways that you can think about figures of merit for moderators. And I guess I'm out of time, so I'll just briefly touch on these two slides when we come back tomorrow, and then we'll also that'll basically be the end of chapter 4. And next class we'll touch up on those last two slides, and then we'll get into chapter 5, which is about heterogeneous reactors. When we talk about heterogeneous reactors, that'll give us everything that we would need to start doing the reactor design problem. So once we finish the chapter 5, I'll release the reactor design problem, and then y'all will have basically from when I release it to like the week before the final to do that. Um, and so, yeah, thank you all for your time. Hope you all have a good rest of your day. Hope you have a good weekend. If you have questions, let me know. And if not, I'll see y'all next week. Do you know when you do the finals? It is